Okay, so let me quickly share my screen. Okay, so uh, I'm going to give a very high level view on why there are so many security issues and basically kind of a motivation for the course itself in this lecture, right? To begin with, popularly there are three walls in computer architecture. Walls, as they typically represents, they are hurdles, and these three hurdles that were present for the computer architects, they have impacted a lot of the design choices across the years, right? Just one second. I think there's an issue. Just one second. I'm going to share my screen again. Do let me know if you're able to see it. Uh, okay, can everyone see my screen?
Yes, it is visible.
Yes, sir.
Yeah, thank you, thank you. So, as I was mentioning, the three walls had a lot of impact on the design choices the architects made across the years, and the all the designs that we currently have were addressing these walls in one way or another. Now, they're popularly called as the power wall, the instruction level parallelism ILP wall, and the last one is memory wall. Okay. Now we'll start by looking at the power. Primarily, everyone was concerned about the dynamic power, and the calculation is given by the product of the capacitive load that is switched whenever we are trying to perform an operation times the square of the voltage times the frequency of operation, CV square, F, right? So the and dynamic power by its definition is the power consumed due to the transistor switching whenever we are performing an operation, and how the how one circuit or one transistor is loading the other circuits and transistors. Primarily it's called load, right? And if we look at the dynamic power, we can say that it is the useful power, uh, and the reason being, even though the power is getting consumed, it is primarily doing the task that we want to do, right? The other component of the power is static power, and this power is consumed when the transistor is just on. It's not specifically doing anything, but just to keep it on, we would require to supply at least this much amount of power. Okay. Now this as a equivalent component of useful power, this will be the one which is primarily uh, uh, not so useful, I should say, because we are not performing any task, but it will still be useful because we would require to uh, save the state of the program in the memory, right? And the static power is proportional to the number of transistors that are on at any given point of time. And the earlier technology notes, right in 1960s 70s time, the number of transistors were very few, so the static power consumed by these transistors was quite small. And within the static power, the leakage power is the major contributor. And if we look at across many technology nodes starting from 180 nanometer to 70 nanometer, and for different temperatures on the x-axis, right, from 298 Kelvin to 373 Kelvin, right, we can see the contribution of static power slowly increasing with the temperature, right? And with technology node also, the static power component is increasing for any given temperature, right? So the static power started becoming more a bigger headache in the newer generations, and in this point implies that we can no longer take the static power for granted, and we have to account it even in the designs. Now, during the same time when Moore's law was proposed, Dennard has proposed another uh, observation. It's not proposal; it was an observation that he made, saying that with every technology scaling, right, the transistor density will double. It means that the number of transistors for a given area will keep multiplying by 2, and the frequency of operation will become 40% higher than the previous generation, and the power consumption will remain same. So this is the key part of his observation, saying that the power consumption is likely to be remaining same because the voltage will also scale. And if you remember the dynamic voltage, half CV square F, right? The even though the F frequency is increasing and the C, the number of transistors that would be overall contributing to the capacitive load will increase, it will be negated by the decrease in the voltage. That was the primary observation that Dennard made, right? And this implies that the power density remains same. Power density meaning the amount of power we are uh, dissipating or consuming for a given area. Now, how does it impact the system design is based on the power density we uh, prepare the or design the cooling equipment. If you typically open your laptop or desktop, there will be a fan which will be sucking out all the heat and uh, you know blowing it out, right? Also, there are some liquid cooled uh, 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 designs where even though there is no explicit fan, this liquid gets absorbs all the heat that is getting generated by the processor. Now, because the from techno with the technology scaling, the processor chips are coming up with more capability, meaning that more compute capability and faster. But we still are okay with cooling equipment that was working few years back. The cost of development overall was quite less, right? But what happened is Dennard assumed that the voltage scaling that will happen with the transistor size is linear, but that was not the case. So the dynamic power was not scaling as much as the size of the transistor itself, right? Also, Dennard made another mistake of overlooking the leakage. Like I said, during the time this observation was made, the static power was not a major contributor. So what happened with all this is the Dennard scaling failed. There are two implications of it. The implications being, with technology scaling, we cannot switch the transistors faster, meaning that the frequency scale up is not happening. The other implication is, even though we have billions of transistors on the chip, we cannot switch on all of them or work with all of them at the same time, because the amount of power, either the dynamic or static power that they are going to consume or dissipate, it will be too much. Then our cooling equipment will not be able to handle it, resulting in the burning of the chip itself. Right? This is popularly called as the power wall. And during the time of around 2000, early 2000s, there was an estimate that if the power consumption will continue, this graph shows that the power consumption, the watts per centimeter square, this is the power density across different technology nodes. Right? These are i386, i486, Pentium Pro, and here is the Pentium 4 processor, right? So the observation was, if we continue like this, the amount of power dissipated will be very high, comparable to the sun's surface. And almost at the same time, there were a lot of studies that were happening, showing practically how much power is being dissipated by the processor. And here you see that someone is trying to make an omelette on the heat sink, which was placed above the Pentium 4 processor. In fact, there were a couple of other experiments where they were making some noodles and all that. So what happened with during this time frame is, people realized that they cannot take power for granted, and they started having power aware designs. Okay. So for handling the dynamic power, one of the straightforward decision was, let's not keep increasing the frequency, right? And for that, if you look at the graph on the right side, across different generations of Intel, products, starting from 80286 through Core i5, which is the Ivy Bridge microarchitecture released in 2012, you can see that the clock rate somewhere increased till 3.6 gig, and even 4 gig almost during the 2004 itself. But after that, it has tapered down. We are not aggressively scaling the frequency. And the black line is the power. And the earlier figure that I showed, where someone was making omelette, was on Pentium 4, where the power consumption, the power density rather, was very high, right? So after that, somewhere in 2004, the power aware designs came into the picture. So we had some more techniques like DVFS, which expands to dynamic voltage and frequency scaling. So a quick point on this is, it when the processor is not being used heavily, the DVFS module, what it does, it will reduce both the voltage and frequency of operation, so that the static power will also reduce. And when the workload is very compute intense, then the maximum voltage and maximum frequency would be allowed. Right? And there was a popular study on AMD Optron, right, on the amount of savings in power that DVFS was able to give. So nearly 20% of savings were obtained. And following the same pattern, there were a lot of low power modes that came into the existence. Right now, even if you look at your mobile screen, it will turn off after a few seconds, or based on the setting that you do. And even your laptop or desktop screen goes to some screensaver mode or something like that. So this is one classic example of low power mode. Why do we want to burn power when it's not being used? Right? Such low power modules are almost present in at various levels of microarchitecture, and even the memory. And overall, these were the power aware designs that were coming into existence. And there were more techniques like clock gating. Clock gating meaning you stop the clock, supplying the clock to the module if it is not under use. Then we have power gating as the possible solution to handle static power. So power gating means that we are not going to supply power to some circuit or a module which is not currently under use. We are going to shut it down completely. Shutting it down was synonymous to the dark silicon, right? If you take a snapshot of the temperature profile of the processor, right? So the part where the power was not supplied will show up as black typically, and the ones where the power is being consumed a lot and dissipated a lot will show up as blue and red. So that's where the notion of dark silicon era has begun. Okay, now the second wall is the ILP wall. ILP expands to instruction level parallelism. Now, if you remember your basic computer architecture or organization course, you would have known about this notion of pipelining, right? Where we are trying to overlap the execution of multiple instructions, and what pipelining affects is the throughput, meaning the number of instructions that can be completed in a cycle, in any cycle, will be uh, proportional to the number of pipeline stages, so to say. But there are a lot of hazards and all that, but it will any day be much greater than uh, executing one instruction at a time, right? That is the primary understanding, or the primary motivation for the ILP, instruction level parallelism. So starting from the simple pipelining, right, people have explored a uh, different approaches, right, till 2003 time frame. From a simple scalar in order pipeline, uh, the architects moved to the out of order pipeline, superscalar version of it, and then there were very deep aggressive superscalars, meaning the width and the depth of the pipeline both were quite high, and effectively increasing the number of instructions that can be executed in parallel, right? On top of it, there were the techniques like speculation and multi-threading that help to extract maximum ILP from the existing program. So because of all these techniques, you can see on the graph on the right side that nearly from 1986 through early 2000s, there were nearly 50% improvement in performance for almost all the different type of processes that you can see in the market. But during the time frame where the power wall came into picture, we were not able to get the frequency scaling, etc. Coupled with that, we have hit the ILP wall also. What is this ILP wall? Having a complex pipeline, right, superscalar processor with speculation, multi-threading, etc., was getting problematic. The reason being, the power consumption was becoming very high, and uh, speculation by uh, I'll quickly explain what it is. Let's say we have some control instruction, let's say a branch or a jump instruction. When we start executing that instruction, right, during the first few stages of the pipeline, we don't know that it's a branch or a jump. So but the way pipeline works is, the moment this instruction moves from the fetch stage to the decode stage, next instruction is fetched, meaning that if we realize that we have to take a jump, or we have to branch off to some different instruction rather than going in sequence, then whatever we have fetched, the few cycles till then would be wasted, right? So because of that, the notion of branch prediction has come, and that was further developed to be speculation, right? Instead of waiting for the branch to be actually resolved, saying that whether we have to continue sequentially or we have to jump to some target address, we make a informed guess, saying that maybe we will continue with the target, right? And so like that, the performance was achieved whenever our speculation was correct. So we are not losing any cycles nor flushing any instructions, right? But what happened with these complex pipelines is the speculation cost, the misspeculation cost was increasing. Why? The uh, the reason being, the time between our prediction and the time by which we can actually resolve the branch and get the actual direction of the branch, whether it is sequential or some target address, was uh, uh, was too much to handle. Means we are flushing too many instructions, and that too frequently. So this has resulted in not so much increase in the ILP, right? And then we have also hit the point where more and more uh, hardware dedicated to increasing the number of pipeline stages was not resulting in performance. So this popularly is called as the law of diminishing returns. In general, you'll observe in uh, uh, any physical activity, the only till some point you will get you can extract the maximum of the work that you are doing, but beyond that, if you keep pushing, whatever you get is very limited, right? So because of all this, the approach of the designers has changed. Till then we were trying to build a very complex processor. Then we realized that it's not going to help us, meaning that with technology scaling, whatever transistors that we are getting extra from one generation to another generation, we should use them more uh, uh, intelligently. So what happened is, excuse me, two primary approaches were taken. One is increasing the number of cores on a single chip. So to address this ILP wall, right, we have moved from a single core processor to multi-core processor. And till the point where the single core processor was there, all the software development that was happening was unaware of what exactly the hardware was doing. They were happy, the programmers were happy that they are getting a faster hardware every 1.5 2 years, right? And what happened when we moved from single core to multi-core is the way we develop our programs has changed. So now we think right from the time we start writing programs, we think on how we can run them in parallel as multiple threads on multiple cores. So that was a major impact on the software community, right? It also resulted in increase of on-chip cache capacity, right? Caches, as you are aware, store the frequently used data, right? And multiple cores are there, so all the cores can use this cache to sustain the uh, increased accesses, because now the accesses are increasing because multiple programs are running simultaneously. So all of them will have the fetch and load and store accesses coming to the caches. So to handle multiple of these, we have increased cache capacity and increased cache bandwidth also. Of course, this has helped only to a certain extent, but it's not so small that we can neglect it. So that's when, like I said, from single core to multi-core, we have gone. It was primarily driven by the power law and sorry, the power wall and the ILP wall. In addition, the time we were taking to scale the transistors across the generations was also increasing, right? Recently, if you have observed news over the past few years, Intel was not able to come up with the chips, the new processors on their scheduled time, because they were not able to scale to 7 nanometer. AMD was the first to scale to 7 nanometer, and they were the ones who released the processor in the market with 7 nanometer technology. So the Moore's law was slowing down, the ILP wall was hit, and the power wall was also hit, right? So during the mid 2000s, there was a notion that instead of hiring one horse, we will hire hundreds of rabbits to do its work, right? The third wall is the memory wall, right? And it's primarily because the speed at which the CPU development was happening was not matching with the speed at which the DRAM development was happening. Meaning, development in the sense the speed of operation of the CPU was improving almost by 60% every year, but the DRAM speed of operation was improving only 7% in a year. So because of that, across years, there was a widening gap, and this is the memory wall, right? And so if the conventional memory wall definition is the latency of the memory is too high when compared to the latency of operations within the CPU, right? So to handle this conventional memory wall, one popular approach was to build a hierarchy of memories, right? In the current processors, we have multiple levels of caches, right? 2 to 3 levels are very common, and some of the processors have L4 also. And some of the processors have more than one level of main memory, and it can be a combination of the typical DRAM plus some non-volatile memory technology like STT-MRAM or PCM or 3D crosspoint, etc. And we also have two levels of main memory, secondary memory. One is the fast secondary memory, which is based on solid state devices, and the second is the slower secondary memory, which is based on the magnetic devices, right? The typical hard disk. And why this entire hierarchy of memories works is because the applications were exhibiting high amount of locality, right? Principle of locality, as they call, has two aspects to it. One is the spatial locality, other is the temporal locality. So spatial locality says that if the program is currently using a location X, then there is a high chance that the nearby locations, say X plus 1, X plus 2, or X minus 1, X minus 2, etc., will be used. So it is better to get not only X with us, but a group of neighboring bytes also. And what does the temporal locality say is, if the program is currently using the data in location X, there is high likely chance that it would require X in near future. So heavily building on the principle of locality, the entire memory hierarchy was built, and this to some extent has solved the memory wall. But what happened was this is not sufficient. And during the time frame when we moved from the single core to multi-core, the memory wall has resurfaced. The reason being, when we moved from single core to multi-core, the number of accesses that the caches and main memory are proportional to the number of cores that are fabricated, right? Earlier, only one program or one thread was running on single core, but now we have 4 cores and 8 cores. Effectively, there can be 8 times the number of accesses, and not only the numbers, it also increases the demand on the bandwidth, meaning that we can get increased number of requests at any given time, right? So this has led to a lot of destructive interference at the cache and memory, right? What this implies is the cache being a shared resource. Let's say you have an 8 MB cache, right? And there are 2 programs that are using the same cache. One of the program needs more than 4 MB. It means it will take the space from the other programs, right, in the cache. So this was resulting in one program kicking out the blocks of other program, so on and so forth. And because we were moving from single core to multi-core, the software developers started visualizing the code as multi-threaded programs, meaning that the program can be run in parallel in multiple stages, but every now and then we need to sync up, right? Also, these threads can require to share the same data. So this resulted in coherency issues, and that can additional result in more misses. So the third point I have already covered, saying that we would require more bandwidth also. So even with this, we still note that almost 50% of our current day processors is devoted to on-chip caches like L1, L2, and L3. Along with this movement from single core to multi-core, the other thing that affected memory wall was the nature of applications itself, right? If like I said, the entire memory hierarchy was built on locality of principle of locality, but the current day applications exhibit very less locality, meaning that more or less for most of the requests or data requests from the core, we would end up going to the main memory or the secondary memory. In that case, even though caches are there in the hardware, they might not be able to cache anything. Right? So its scope is very limited, and the size of the applications has also increased over time. Because of that, the caches that we have in the current process are no longer holding the working set of the application. Working set meaning the code on which the application spends most of the time. Typically, it is a few set of loops, etc. Right? For also the interconnections between the cores, because we have multi-cores, right? They can interact with each other, and the caches are also split, and the memory that is now currently being shared by all the cores, etc., need to be more and more scalable in terms of bandwidth. So the modern memory wall is where both latency of the memory and the bandwidth are critical. Right? Now, how are we handling this modern memory wall is we are making the cache and the memory levels more and more adaptive to the programs that they are running. So in the previous example where I mentioned that one program needs a lot of cache space and other program is happy with some of it, for example, right? Instead of dividing the cache uniformly, we can divide the cache proportional to the usage of the program. In that way, the same limited cache can be effectively used, right? Now, another approach was in-memory or near-memory computing, right? As the cache itself is becoming more or less useless, both because of less locality and application footprint, there was a popular thought on why not bring the memory itself closer to the memory. Memory itself closer to the processor. So that's where the notion of near memory computing has come. Also, the other way of looking at it is we can do some computation within the memory module itself, right? That is the in-memory computing. And there are a lot of accelerators that were developed with this approach. And if instead of the traditional DRAM, some new DRAM technologies were developed so that more and more high capacity DRAM can be brought closer to the CPU and the GPU in general, right? We have the hybrid memory cubes and high bandwidth memory, HMC and HBM, they are popularly called as. Right? Now, with all these three walls, what happened is we have the current day processor designed in a particular way to handle them, right? That has resulted in possibly the fourth wall, which is security. Why is it important now? If the questions are like, is our data vulnerable? Is the situation so bad that we need to consider security? Right? We do consider security in our day-to-day operation, activities, right? We think twice before we are using any, publicly available Wi-Fi network. For example, in the malls or in airports, we don't directly connect to it by default. We are skeptic that somebody might be supervising the data that we are trying. send and receive, right? And before we download any app, we go and check who is the author of the developer of the app, how many people have used, what are the reviews, etc., right? And before we are making any online payment, we check the link, HTTP link once or twice, right? And even when we are reading the emails, and if there is a image embedded in the email, we think twice before loading it. Or when we are replying to somebody whose email ID which we are not able to recognize, right, we check for that. And whenever we are trying to create a password now, you can see that it has become very complex, that it needs 8 or 10 characters. There should be one capital letter, one small letter, one alphanumeric letter, etc., right? All these. And it's not only once, but we need to change such passwords for every 3 or 4 months. And when we are entering the pin in the ATM, we check twice that there is nobody overlooking our shoulder, or maybe the CC camera in the ATM is directly pointing to the keypad, etc. We should be purview of of all such small things. And in general, whenever we are trying to give our mobile, or the pen drive or laptop, etc., to anybody whom we are not too much acquainted with, we think twice. And of late, because of the crisis with our neighboring country, we also check whether the product that we are purchasing is from that country or not. So security is not new, but it is new in the context of hardware, or it has been there in the hardware, but it was handled to some extent. But now it has become more and more serious, because now our hardware is connected to multiple devices across. That has been propelled by the uh, increase in the connectivity overall. From we have currently the 5G, etc., right? With increased speeds and increased capability. And no longer the hardware is a private resource, right? It is a shared resource at different levels. You can actually make your PC part of a cloud and rent it out. It is quite possible. Or if you consider your mobile phone, there are multiple devices that are using it simultaneously, right? And if you consider a single processor, there are multiple cores in that processor, and all these cores are sharing some of the resources like caches and the interconnection network, etc. And even within one core, we have the notion of multi-threaded uh, cores, right, where multiple threads from the same program or different programs can share the resources within a single core, right from the reorder buffer to the caches. And all these choices that we have made were primarily were to address the previous three walls at the hardware perspective. Can we say that the design choices we made earlier were bad? No, but they had uh, some vulnerabilities that we overlooked. But now we can no longer overlook them, because they can act as backdoors for the attackers. So that is the reason we need to be more and more security uh, aware with our newer hardware. Whatever small optimization that you are bringing up, or the entire processor that you are building, it should be security aware. So we had power aware designs, memory aware designs, and ILP aware designs. Now is the time where we have an superset of them, which is saying that we also need to take care of security. And in addition to the ones I have listed here, the first three, we have the technology scaling, resulting in more and more vulnerable hardware, meaning that the transistors that are switching very fast are very small. So we can trigger some stray actions on them, just by changing the voltage of the neighboring cells. For example, in the DRAM, we can affect the value that is stored in this cell. And that's the popular row hammer attack. This imagine the row hammer attack on a hybrid memory cube. Now, a DRAM is you can imagine it to be a two-dimensional array of DRAM cells, but hybrid memory cube or high bandwidth memory are a 3D arrangement. It means that the row hammer can potentially affect multiple rows. If you imagine a cube, right, there will be victim rows all across. Such a thing was possible, integrating multiple layers, etc., one on top of each other. It was possible with improvements in the technology scaling. So with newer designs, we have high capability hardware, but it is also prone to more attacks. So this course is primarily to make the hardware design aware of various security issues, right? We will study both the attacks and defenses at various modules, right? And all these attacks will be studied in specific lines. We'll try to understand them, how they are affecting in three specific parameters, right? The first one is confidentiality, meaning that if your data should not be allowed to be accessed until and unless you allow it. So until and unless the user allows that somebody else can read or write the data, it should not be changed, or it should not be even read to begin with, right? Integrity is where only the authorized user can change the data, nobody else, right? And even when there is a change, the user should be able to trace it back. That is the integrity. And the third is the availability part, wherein whenever the user wants the data, it should be available to him. So there are many security attacks that can be affecting one or two or all the three aspects of the data. And in addition, we will also see a few threat models. Threat models means how is the attacker able to launch an attack? What is the setup that he is using, and what all information does he have? For example, on if you look at the ransomware, the threat model is primarily a malware that was installed by mistake by the user. Either it can be part of an email or anything like that. But the moment it gets installed, it will encrypt your entire hard drive. Right? That is the threat model for ransomware. But when we are looking at the retrieval of some deleted data, for this, one can only retrieve the data only when he can possess the disk uh, physically. He cannot do such retrieval from in a remote fashion, like the ransomware attack. So these are the threat models. So the attacker is assumed to know some information, and he is also assumed to have some access to the hardware, right, etc. So we'll also study each attack with the threat model in mind. Okay. So with that, I conclude this lecture. Any questions? Any questions?
Hello, sir.
Yes, Rohit.
Sir, could you please go back to the Dennard scaling that PPT, sir?
Okay, 1 second. Okay. Yeah. Which slide?
One which explained it, sir. Okay, sir. Over here, it says like if we given a surface area, in every generation the density doubles
Right.
and the power consumption stays the same. So for this to happen, the power consumption of each transistor should get halved, right?
Yes. How will that get half is with the scaling in the voltage.
Okay, like every generation, the voltage also kind of decreases
Should be
like that.
scaled proportionally. Yes.
Okay, okay, got it.
So
Thank you, sir.
yeah, but that did not happen. It was scaling. Earlier we had devices which work on 10 volts and 5 volts, but now we have devices which work at 1 volt also, right? So that's how
Okay, sir.
the voltage scaling was happening, but it was not proportional to the transistor scaling.
Okay, sir. Thank you,
Yeah,
sir.
yeah. Any other questions?
Sir, is the leakage mentioned in this slide is same as static power consumption?
Yes, leakage is part of the static power.
Oh,
Yeah, there are actually different types of leakage powers also. One that is, if you have a single transistor in mind, there is leakage from the source to drain, there is leakage from the gate to source, gate to drain, etc.
okay.
Yeah. Okay, anything else? Okay, so in the coming week, our TA Vakar will present the basics of the solid state drives. He'll also present various attacks that are possible. Specifically, he will dive into the ransomware attack, and he will also give a demonstration. Okay, so please join the same link. We'll continue using this link till the next few weeks, until the online thing is, we'll get a clarity on that. Okay. Okay, I've stopped the recording.